So far in our explorations of physics, we've been focusing on a very specific thing. We've been focusing on motion that occurs when a force is in the same line as the motion that is occurring. So either there was no force at all, so the lines of motion didn't matter because an object was just moving at a constant speed, or was at rest because there was no net force acting on it, or when we resolved all of the forces into component vectors, we had one dimension that canceled out, and the other dimension had a force, a net force, that was pointing in the same line as motion, either in the same direction as motion, forward, accelerating the object forward, or upward or downward, or in the opposite direction of motion. Still in the same line as motion, but in the opposite direction, causing a negative acceleration, causing an object to slow down or possibly to speed up, but in a backwards direction. That's what we've been learning about so far. But do forces ever occur outside the line of motion? Now, we've dealt with a lot of forces that were outside the line of motion, but keep in mind what we did with those forces. We broke them into components, we worked with them as vector sums, and we resolved them. So they always turned into forces that canceled in one dimension and then a net force in the direction of motion. Do forces exist outside of the direction of motion? And if they do, what do they cause to happen? Well, that's what we're going to be learning about in this lesson. Yes, forces do exist that act outside of the line of motion, and those forces cause centripetal acceleration, and we call those forces centripetal forces. All right, so let's dive into that definition of a centripetal force. Now, we talked about forces in the direction of motion. These are non-centripetal forces. A net force in the direction of motion, in the line of motion, causes an object to speed up or slow down. But a net force perpendicular to the line of motion causes an object to turn. So that's the very first thing you need to know about a centripetal force. Anytime an object turns from its straight line path, it must be affected by a centripetal force to do that. It's not necessarily going to move in a perfect circle. We're going to talk about the conditions necessary for an object to move in a circle. But if an object is turning, there must be a centripetal force acting on the object. So here we have a typical view that we would have looked at of a car moving in a certain line of motion in one of the units so far. Notice we're looking at the car from a side view, and what we would typically do with this is put a free body diagram either over the car or next to the car, and we would envision the forces that are acting. Notice that the forces in one dimension cancel. In the vertical dimension, normal force cancels with the force of gravity. That happens all the time in real life where forces in one dimension cancel, and we just have forces in a different dimension that are accelerating an object in the line of motion. In this case, that's what's happening here. The friction force of the tires acting against the road are actually pushing the car forward because they're resisting sliding between the tire and the road. And then there's some rolling resistance and the imperfections in the tires and the axle and things like that. So we have this forward force, a rearward force, and those two are not going to perfectly cancel out. We're going to end up with a net forward force causing a forward acceleration. Now, in this unit, we're going to start looking at our objects from different angles. It's not always going to be a side view, because in the side view, there's a dimension that we can't see. We can't see what's called the z dimension. We see the x dimension, horizontal, the y dimension, vertical, but there's also a z dimension of depth, and we haven't really worried about that yet. That means that in the z dimension, either there were no forces or the forces were always balanced anyway, so we didn't have to consider it. But now we're going to be considering what happens when forces act toward the side. Okay, once again, we can look at a top view of our car, and if these are the only forces that are acting, my friction force pointing forward and my rolling resistance force acting backward, notice from this view, I can't see the vertical forces. But once again, the vertical forces don't really matter because they perfectly cancel each other out. All of the forces are in the line of motion. But now we get to a force outside the line of motion. What happens when you turn the steering wheel of the car and suddenly in that z dimension, from the side view of the car, the z dimension, the forces are unbalanced. And now I have a friction force that points at a diagonal to the line of motion. Well, let's just analyze this the way we would analyze any vector. So I'm going to go ahead and add my friction force vector to my rolling resistance vector, and notice I get a net force pointing off to the side. That net force is very close to my original friction force vector because that rolling resistance vector is very short. So I've got this vector that's pointing partially in the line of motion, but partially perpendicular to the line of motion. And I can actually break apart this vector and look at the part that's in the line of motion and the part that's perpendicular to the line of motion. I'm just going to call that the z dimension force, because again, if I'm looking at this from the side, I'm looking at the depth axis. Okay, so these are the forces that are acting, and that F net x component of my net force is going to accelerate the car forward. But what is that F net z force going to do? So I've got this forward acceleration in the direction of F net x, but I also have an acceleration off to the side. And what that's going to cause to happen, this car is actually going to turn. Now notice that it's not turning in a perfect circle. That's not a circular path because there's a forward acceleration as well as a sideways acceleration. So it's going to be moving in sort of an oblong path, sort of an oval-shaped path. And that's just the characteristic of when I have a car that's accelerating forward and to the side. Now, when would this happen in real life? This would happen in real life if you come to a stop sign and you're turning left. So you stop at the stop sign, then you accelerate forward from the stop sign when it's your turn to go, but you also have to turn your wheels of your car to the left. So you both speed up and you turn around the corner. And because you're speeding up in the direction of the motion of the car and you're turning around the corner, your path actually looks sort of like an oval type path. It's just an arc of an oval, but it looks like an oval shaped path as you're moving. All right, at this point, we're ready to define what centripetal means. Anytime you have a force or acceleration perpendicular to the line of motion of an object. So you assume that an object moving is going to move in a straight line, and if it doesn't move in a straight line, there must be a centripetal force and centripetal acceleration being applied. And all that means is you have a force or acceleration that's perpendicular to the natural straight line of motion. Why is that straight line of motion natural? Well, remember Newton's second law of motion. Newton's second law says that an object at rest remains at rest. We don't care about that part. But an object in motion stays in motion in a straight line at a constant speed unless acted on by an outside force. Now, we've talked a lot about how the speed changes with acceleration. Now we're talking about how that straight line can change with acceleration as well. That's what centripetal acceleration does. And then it's also important to note that centripetal acceleration can cause objects to move in perfect circles. If you have a constant perpendicular centripetal force, and what that means is the only force that's acting is a perpendicular centripetal force. There's no forward force like we had with our car just a moment ago as it was speeding up from rest at a stop sign, so it was moving in an oval. If the only force that's acting is a constant perpendicular centripetal force, that causes an object to move in a circle. Now, what has to be true about that force? Well, it has to be constant, the same size, and it has to be constantly perpendicular. So the direction of the force has to be constantly pointing toward the center of the circle. That means that the force's direction has to constantly change as the object moves in a circle. Well, what kind of forces even do that? Well, actually, in the real world, there's quite a few forces that act in this way, causing objects to move circularly. For example, if you're in a car and you're driving in circles, you can drive in circles in your car by applying a constant friction force toward the center of the circle. Now, I don't know, apart from being on a circular racetrack, maybe this isn't a great real-world example because you don't usually drive your car in perfect circles. But what you do typically do in a car is you turn from one corner to a perpendicular corner. And if you do that at a constant speed moving around the corner, you're actually experiencing a centripetal circular motion around a quarter of a circle. Now again, that has to happen where you're moving in a circular path and moving at a constant speed around the circle. But that actually does happen. You could also maybe do a U-turn where you go halfway around the circle at a constant speed. Okay, so there's a real-world example. And pay attention the next time you're turning in a car, because at that moment you're experiencing centripetal acceleration and centripetal force. Another example is anything that you swing over your head. Now, a typical experiment that you do in physics is you take a rubber stopper and tie it to a string and swing it around over your head to experience centripetal forces. The tension of the string is always pointing toward your hand at the center of the circle, so you always have a force pointed toward the center of the circle, and it's constantly changing directions as the rubber stopper moves around the circle. And you could imagine anything that you swing over your head on a rope would be this type of centripetal force. Another example is happening right now, and maybe you're not even aware that it's happening right now, but as the moon orbits the Earth, and on a larger scale, more imperfect scale too, as the Earth orbits around the sun, we've got centripetal accelerations and centripetal forces at play. What's happening as the moon moves around the Earth? Well, it's moving in a circular path and being pulled inward by the force of gravity. And because it's moving around the Earth and the Earth is constantly pulling on it, that direction of the force is constantly changing and pointing toward the center of the circle as it moves around the circle. Always pointing toward the center of the circle, but it's always changing with respect to the moon. And the moon ends up moving in a constant speed in a fairly circular path around the Earth. All right, let's take a look at another example, and this one's going to be a bonus video example. Here, I have a video of a ride at an amusement park. Maybe you've been on a ride like this. I used to live near an amusement park. We had a ride like this called the Cajun Cliffhanger. And actually, somebody got badly injured on the ride somehow. I think they were doing something they shouldn't have been, but there were lawsuits, and the ride ended up getting closed down. But look what's happening. These people are being forced to move in circles by the wall behind them. The wall is pushing on them, and look what happens at the end of this ride. The floor can drop out from below their feet. In just a moment, you'll see that happening. And look what happens to the people who are riding. There it is. Now, notice there is no floor below their feet anymore, and yet they are sticking to the wall. Can you picture what force is holding them up, preventing them from falling down? And if you can picture what force that is, can you imagine what force the wall must be applying to them? Well, let's look at this in the same context as we looked at other forces. So here I have my wall around the outside. Here I have my person moving in a circle. And what force is pushing this person in toward the center of the circle? Well, it actually happens to be the normal force from the wall behind the people. And because it's a normal force being applied from a surface, there could also be a friction force perpendicular to the normal force, and that's the force that was actually holding the people up above the floor. There was friction between them and the wall, and they weren't sliding down the wall, they were sticking to it instead. Okay, so we've got all of these different examples of forces that we would call centripetal forces. Now, this is an important lesson for you. Centripetal force is never a force in and of itself. Okay, it's not like a different new kind of force that we're identifying. Centripetal force just means that a force that's caused by some agent that's identifiable, and it's going to be the same sorts of agents we've been working with this whole time. You see down below there's friction, tension, gravity, normal force, and there could be others as well. But some force is being applied toward the perpendicular to the direction of motion. We could say toward the center of a circle, okay? And that force that's being applied is causing an object to turn and change direction. But a centripetal force is not its own type of force. It's always a different type of force that has the characteristic of being centripetal. All right, one other point of interest. You notice in the diagrams I have at the bottom of this slide, there's always one force that's pointing in toward the center of the circle, and that's the centripetal force. Well, it doesn't always work that way, but a lot of times in the real world, it does. A lot of times when there's a centripetal force, it's actually just one force with one agent that's pointing toward the center of the circle. And we would say that because there's just one force acting in that dimension, that one force is the net force. So friction force in the first example was the net force. Tension force was the net force in the next one, and so on. There can be a sum of forces that point toward the center of a circle, and the sum of those forces equals the net force that is the centripetal force. That does happen sometimes. A lot of the problems we're going to work, though, and focus in on are just going to have a single force pointing toward the center of the circle, not a vector sum of forces that are perpendicular direction of motion that cause the centripetal force. But it is important to note that the net force is what is centripetal. It's not just, again, it's not just an individual force, and it's definitely not a special kind of force that's called like the centripetal force. It's always caused by typical forces with identifiable agents. And the point here is that sometimes it's caused by multiple forces added together whose vector sum points toward the center of a circle. Next, I have a question. What happens if the centripetal force acting on an object, pulling it toward the center of a circle, suddenly ceases? There is no more centripetal force. It ceases to exist. How is the object that was moving in a circle going to move once the centripetal force stops acting? Well, I have a couple of videos to show you that demonstrate how the motion of an object carries on when it's no longer connected to the thing that's moving in a circle, or when there is no more centripetal force acting on it. First of all, let's take a look at this bike tire being sprayed by a hose. Look at the direction that the droplets are moving off of the bike tire. Do you notice that they're moving at a tangent to the circle? That means that at the outer edge of the circle, wherever the radius is pointing toward the very outer edge of the circle, these objects are flying off perpendicular to the radius. So right off the edge of the circle. And you can see that these are moving tangentially, we would say. So perpendicular to the radius of the circle. We're going to make sense of that in just a bit, but first let's look at another example of the same sort of thing. So these water droplets were clinging to the bicycle wheel. There's forces that hold the water droplets to the wheel, but eventually they couldn't hold on anymore because the wheel was turning too quickly. There wasn't enough centripetal force to maintain their connection. And when they leave the wheel, notice the direction that they move. It's always at a tangent to the circle from the point they leave from. All right, let's look at another example of metal sparks flying off the end of a sparkler that's attached to a drill. Because this gives another example. Notice the direction that the sparks are moving. When they are no longer connected to the sparkler, they're always flying off at a tangent to the circle. So this should give you a clue as to what happens if something is moving in a circular motion because it has centripetal force. And there's no other forces, no other net forces acting on the object other than the centripetal force. This is going to tell you what's going to happen if that centripetal force were to suddenly cease. What direction would the object move? Well, let's also consider Newton's first law of motion, because this helps us explain it. An object at rest remains at rest. Again, we don't really care about that part because we're not talking about objects at rest. We're talking about objects moving in circles. But a moving object moves in a straight line at a constant speed. That's its natural tendency. That's what its inertia causes it to do. Straight line at a constant speed unless acted on by an external net force. Now again, previously we talked a lot about what happens to that speed as the result of an external net force. An object speeding up or slowing down as a result of a force in the line of motion. Now we're talking about what happens when there's a force perpendicular to the line of motion. The object is no longer going to move in a straight line. It's going to change direction. So what happens if that force suddenly ceases? There is no more centripetal force. How is the object going to move? Well, it's going to move at a straight line in the direction that it is currently moving. So for a stopper that's moving around in a circle, if we suddenly let go of the stopper, or if the string no longer supports with a stopper with a tension force pointed toward the center of the circle, where's it going to go? It's just going to keep flying in the same direction that it was moving when the tension was released. And that's what we observe in the real world with centripetal forces. Centripetal forces cause objects to move in a circle. Once the centripetal force is no longer being applied, the object moves in a straight line at a constant speed. Okay, now we understand enough about centripetal motion to derive an equation related to centripetal acceleration and centripetal force. And the way that we're going to do that is we're going to envision any of the objects that we've talked about so far moving in a circle. And this could be any of the objects we've talked about so far as long as they're moving in a uniform circle at a constant speed around the circle. And we're going to consider two different positions. So here's radius, the original, and then the radius final, okay? So we're starting with one position and moving to the other. And then I can envision the speed at those two positions. And what is the speed going to look like? The actual, not just the speed, but also the direction of it. What is the velocity vector going to look like of the object moving around the circle at the original radius? Do you understand it's going to be moving perpendicular to the radius, so at a tangent to the circle? There I have my original velocity and then the final velocity. And then would I say that the velocity here is changing? Well, absolutely the velocity is changing because remember, velocity is speed and direction. The speed hasn't changed, but the velocity's changed because the direction's changed. And that's what circular motion is. It's a constant changing of the direction of motion of an object due to a force pointing toward the center of a circle. Okay, now let's just do a little bit of geometry with this. We're going to use some geometry of this drawing in just a little bit. So we're going to do some geometry. We're not going to use it right away. We're just going to note it for now. And what I'm going to do is I'm going to note that there is an angle between these two radii. We've moved through a certain angle. Also, I'm going to extend our velocity vector, the final velocity vector, backwards. I'm just going to draw a green dotted line so that is not a part of the vector, but it's just tracing that vector backwards. And then I'm going to note that that makes an angle with the original velocity vector over here. And I'm going to call that angle theta prime. Now, why theta prime? Because it's the complement of theta. Do you see that I have a quadrilateral drawn here on the page? And two angles in my quadrilateral are right angles. 90 degrees and 90 degrees. Well, when I add up all of the angles in a quadrilateral, they have to add up to 360 degrees. So if I have two 90-degree angles, that takes up 180. Then I have a theta in the center. That means that whatever angle is opposite my theta has to be whatever the supplement is. So when I add it to theta, it equals 180 degrees, and I have a total of 360 in my quadrilateral. So that should make sense geometrically. And then look at that theta prime angle, and you notice that that theta prime angle actually sits on two different identifiable lines. One of those lines can be made by putting another angle here, the green line right there. So do you recognize that that angle has to be theta, because when I add it to theta prime, it has to equal 180 for the line. The other line is the red line of my original velocity vector. And I could put another theta up here. I can also notice that these are on opposite sides of intersecting lines, and that also makes them equal to each other as well. But you should be able to recognize that these angles are where they should be. Okay, and we're just going to use these in a little bit. I needed to put them on here so that you can make sense of some drawings that are coming up right now. All right, the next thing that I'm going to do is I'm just going to note that there is a quantity we can find of the change in velocity. So we said that there's an acceleration. The reason there's acceleration is because there's a change in velocity. We're used to calculating change in velocity by subtracting final speed, an original speed from a final speed, right? That's how we would normally calculate change in velocity. But how do we do it when it's actually just a change in direction? Well, since the magnitudes of the velocities are the same, this object's moving around the circle at the same speed. For me to calculate the direction's impact on the velocity, I have to use a vector sum. Okay, and I have to do the vector math, adding together two vectors, and actually it's vector subtraction, which is adding the opposite of one of my vectors, to get a resultant. And my resultant is going to be delta v. So let's just draw out this vector addition problem, see what happens. Here's my v vector, and here's my VO vector. Okay, this would be v plus VO, because notice I'm drawing VO with its tail starting at the head of the first. But actually I have v minus VO. So I actually have to reverse the direction of VO to get minus VO. And now I have v plus negative VO, or v minus VO. Also, do you notice that this angle here is the same as the angle in the middle of the circle? If we look at the drawing over on the left, do you see how that theta between the direction of vector v and the direction of vector VO, and you can see it right underneath where that green dotted line is and crosses over VO, that angle has to be theta. So it's the same angle as in the center of the circle. Okay, and then I'm also going to have this delta V here. That's my resultant from adding these together, or subtracting them. It's going to start at the head of the first to the tail of the first to the head of the last. The tail of the first to the head of the last. And that's my vector sum for this part. Do you recognize any characteristics of this triangle? Since the magnitude of V is equal to the magnitude of VO, you should recognize that this is an isosceles triangle. That means that those bottom two angles are the same, and then I have theta at the top. All right, now let's do the same thing but with R. I have this equation, delta R, the change in the position, and in this case my position is measured with a radius. The change in the radius is R minus RO. Okay, and again, this is a vector sum, so I have to draw out my vectors. So let's go ahead and do that. Here's R plus RO. And again, I'm going to reverse the direction of RO, but first let me just draw in some angles to make this make sense. So do you see that the angle between the vertical and RO is theta? And this is recognizable right from the middle of the circle. Do you see this is just the angle that's at the middle of the circle, okay? Well, if I take the opposite of RO, because I'm subtracting it, I'm not adding it, notice that that theta is going to be exactly the same as the one above it. And that's just because I have two intersecting lines, and these are opposite angles and intersecting lines. So I have a theta there, R, and negative RO. And then when I finish off this vector sum, I'm going to put delta R starting at the tail of the first to the head of the last. And notice that this is also an isosceles triangle with a top angle of theta, and then I don't know what my bottom angles are. I could come up with an expression for them if I wanted to. I don't need to. But I do know that the side lengths R and RO have the same magnitude. I don't know what the value of delta R is. But now that I've got these theoreticals set up, let's see if we can do a little bit of math with these and make some more sense of this problem. Now, first of all, I just want to point out something that's sort of a point of interest. You see how I have delta R down there? What is that delta R actually telling you? Well, it's the change in position of the object. And if you don't believe me, that's the change in position of the object calculated from R minus RO. Look what happens when I slide it up onto our circle. Do you notice that that vector perfectly points from where the object started to where the object ends? Okay, so I just wanted to point that out, that delta R is a real value. That's the change in position of our object as it moves around the circle. Delta V is the change in velocity because it's changing directions. And then let's go ahead and do some math with these triangles using geometry. These are similar triangles, aren't they? Because they're isosceles triangles with the same top angle. So we know V is not equal to R. Negative VO is not equal to negative RO. But they have to have a correspondence to one another because they're sides on a similar triangle. Okay, so how are sides of a similar triangle related? Well, if I set up a ratio of sides on one triangle, I can make the same statement about the ratio of sides on the other triangle because they're similar. So the ratio of delta V to V on triangle 1 is equal to the ratio of delta R to R on triangle 2. And these are real values, real magnitudes of real vectors that I'm working with here. Now I'm going to do one other thing to this equation. This rotation, this movement around a circle is actually happening in real time. Okay, some time passed. And the same time passed as I changed my velocity as the time that passed as I changed my position. So what I'm going to do is I'm just going to put a time value on the bottom of both sides of this equation. Now, if you're puzzled as to how I can do that, well, think about it this way. In algebra, as long as I do something to one side of the equation, I can do it to the other side. And it's not entirely infeasible that I would include time here because this is happening over time. So it makes sense that I would include time in this equation. Now, you may be able to recognize a couple of values that we've used before in physics. Like, we know that acceleration is change in velocity over change in time. And in this case, that change in velocity is entirely caused by the change in direction of the object. So it's not just any old acceleration. We're talking about a centripetal acceleration, just caused by change in direction. And what we're going to do is, if we have a delta V over T in our equation, we can replace it with A. That's what I'm going to do. See on the left, I have delta V over T. I'm just going to replace that with A, and I'm just going to put a subscript C there to note that that's centripetal acceleration. It's a special acceleration caused just by the change in direction because this object is moving in a circle. All right, I have another value you should recognize here because remember, R is a distance value. And if I have a change in distance or change in position over time, that's a velocity. So I can take that change in R over T and replace it with V. And I'm left with this equation. Well, you may notice also I have like terms on either side of the equation. I have a V on the left in the denominator and a V on the right in the numerator. I can multiply both sides by that V. And I find that acceleration, the centripetal acceleration, is the velocity squared divided by the radius. And again, this is the real radius of a circle. And these velocities are those real tangential outer velocities perpendicular to the radius of the circle. So this is a useful equation for calculating what the centripetal acceleration of an object moving in a circle actually is. All right, let's extend this a little bit. We know some things about circles. Like we know that the distance around the entire outside of a circle is 2 pi times the radius. And we're going to define a new term. The period is the time it takes for an object to make one complete revolution around a circle. So it's the exact time to make one complete revolution. So the object is traveling 2 pi r, that's the distance around the outside of the circle, over t units of time. And we're probably going to use meters for 2 pi r, or maybe centimeters. We're probably going to use seconds for the period. So for objects moving uniformly in circles, you can calculate the velocity around the circle by just dividing the circumference of the circle, 2 pi r, by the period, by the total time to make one complete revolution. If I plug that v, the 2 pi r over t in for v, I'm going to substitute that in for v in our centripetal acceleration equation. Notice that I can simplify this to make a new expression. And the whole expression, 2 pi r over t, is squared. So I'm going to have to square the 2, square the pi, square the r, and square the period. And that's going to give me 4 pi squared r squared over t squared divided by r. I can make one further simplification to this because I have r squared in the numerator, r in the denominator. So that's going to cancel out one of the r's. And another expression for centripetal acceleration, notice this one has the period instead of the velocity. So by just knowing how long it takes the object to make one complete revolution around the circle, I can calculate the centripetal acceleration. I have to know the radius as well, but it's 4 pi squared r over t squared. And that's another important equation for centripetal acceleration. All right, then one final observation. Force is mass times acceleration, and it applies to centripetal motion too. I can identify something called a centripetal force if I take my centripetal accelerations and multiply them by mass. So to find the centripetal force from the velocity around the circle, I just have to multiply both sides by mass of my centripetal acceleration equation, because m times the centripetal acceleration is the centripetal force. And instead of v squared over r, to calculate the centripetal force, I just have to multiply by mass, mv squared over r. And the same is true for my other equation using the period. If I plug in m into the numerator of that equation, I can calculate the centripetal force. So now you know how to calculate centripetal accelerations, centripetal forces. You know what a centripetal acceleration and centripetal force are, how they cause objects to turn, how they point towards the center of a circle, and how an object experiencing only a centripetal force is going to move uniformly in a circular path.